All right, welcome everyone to our week 3 recap video. Well, we have an exam tonight. July 24th, 2019, at least while I'm recording this. So yeah, that's kind of the first order of business. And so before I get into the problems of the day, and kind of to recap over this last week, I thought it'd be a good idea to kind of go over a few exam-related things. So first of all, I'm on our course page, our online.math132.com, and if you go and you click the syllabus, right? There's an entire section dedicated to the midterm, and there's also a section dedicated to the final, right? And actually, we know quite a bit about what the midterm exam will look like, right? So there will be 100 points, quite a few multiple choice questions, right? So there's 15 questions, 5 points each there, typically about 3 questions per page or so. And then there's a couple standard response questions, so things where you have to show out all of your work. You're going to get 2 of those questions at 15 points each. This totals 105 points, but again, the maximum is 100 points, so it's a good problem to have. If you get over 100 points, this does get truncated down. 100 is the maximum, but this does give you a little bit of wiggle room, right? So, I mean, if you make a mistake and you get a few points off of the standard response, or if you get a multiple choice question wrong, you can still get a perfect score, 100 out of 100. Now, the midterm questions, they will differ between students. We have different versions and all that sort of stuff. There's a pool of questions that we pull from, and again, I've already kind of told you guys in a couple places, right, that the online this web work practice midterm, and as well with this practice quiz 2.5 that we have this week, which again is just practice, it doesn't count for your grade. Those two, right, problems can show up there, that we've actually pulled and we've used for the midterm exam. So it's a good idea to be taking a look at those. Those are all multiple choice questions. Again, kind of this, again, aligns very well with what we're doing here. We have lots of multiple choice questions. You do have to be careful with the standard response ones, though. I found in previous years and in previous semesters that sometimes the web work, homework, and as well with these multiple choice questions, you sometimes get into a habit of not showing your work, right? And so it's very important for these standard response questions that you show all of your work and how you got your answer, because usually very few points are actually attributed to, what is the correct final answer, and a lot more of the points are attributed to how do you get that answer, right? What are the steps that you take? What is the calculus that you do in order to actually get that answer? So that's where the majority of the points lie on these standard response ones. So it's again kind of very similar to a lot of these either multiple choice web work questions or just the regular web work questions, but you have to make sure that you're showing all of your work and how you get your answer. All right, so again, this does cover chapters 1 and 2, kind of everything that we've had up until this point. You can't, unfortunately, use notes or books or calculators or anything like that. However, you do get a formula sheet, right? So the formula sheet, I've brought this up in the past couple of videos, but it is posted on our course website here under useful links. You have the midterm formula sheet. I would definitely take a look at this and know exactly what's on the formula sheet and what's not on the formula sheet, right? Because it's not all inclusive, so you do have to still memorize a few things here, but it does take a big chunk out of the things you have to memorize, so it's quite nice in that regard. So okay, the formula sheet's going to be provided for you. You don't need to print and bring one or anything like that. Again, it's provided for you. And again, the big show is tonight from 7 to 8:30. The room's going to be B122 Wells Hall. In fact, I'll go ahead. I wrote it down here. B122 Wells Hall, and that's the on MSU campus here in East Lansing, Michigan. Of course, if you've already made some alternate arrangements, if you're not sufficiently close to campus, right, then don't show up here. Show up to your correct location and correct testing center and all that sort of stuff. All right, I think that's all of my administrative stuff for today. What with the exam coming up here. So let's go ahead and take a look at some questions. I know already that this is going to be a long video, so feel free to skip around and only look at the examples that interest you. You don't have to watch the entire video by any means, but just look at the ones that you find that you still need some help with. So this very first one, example 1, is going to be from 2.6. It's going to be an implicit differentiation question. Next up, example 2, this is going to be a 2.7 question, so these kind of rates of change and these kind of physicsy style questions. Example 3 is going to be 2.8, related rates. How can you relate these derivatives together? And again, these are usually kind of these lengthy, word questions, so we have to do a bit of interpretation and all that good stuff. And then in example 4, this is going to be a 2.9 linearization question. So if you, in your participation survey, we're thinking, I really need some more help with implicit differentiation, make sure you at least take a look at the example 1, and then maybe, as you're studying, if you have some more time, you could also watch me do these other ones. So, and as always, I think it's a good idea to pause the video now even, try the question that I have that you're maybe interested in here, and then you can unpause it and kind of hear the solution explained to you. So I think this is a really good way to use these videos. I find for me, anyway, that, it kind of sticks with me a little bit if I actually try it first. If I just see, okay, here's a question, here's the answer, and I see that very fast, I don't know, it just doesn't make a memorable experience. I have a hard time recalling that when I really need it on the exams and whatnot. So anyway, that's a thought. If you're having a hard time recalling the stuff, in the moment of the exam or on the quiz or stuff like this, I would try, doing the problem here before you see the solution, and that way you have more of an aha moment. It's like, that's how I do it, right? There's a little bit more tension or struggle in there because you tried the problem first. All right, with that all said, let's go ahead and start up on example number 1. Find the equation of the tangent line to this curve at the point 1, 1. So first of all, I know that this is an implicit differentiation problem because we don't have y equals, right? We have an equation here, but in all of our other derivatives before this, we've always had y equals. And implicit differentiation is great because you don't need y equals. You can still figure out slopes of tangent lines and derivatives and all that sort of stuff for any old equation, and you don't need y equals. So that's the power of implicit differentiation. So the very first thing, yes, we need to implicitly differentiate both sides. So let's go ahead and go about this. So I'm going to go ahead, let me do the easy side first, right? The derivative of 6 is 0. Boom. On the left-hand side, okay, this is where we need to use our derivative rule as well. The derivative of x squared is going to be 2x. The derivative of, and this is a product of functions, right? We have 2x times y. So we need to actually use the product rule here with our implicit differentiation. So I'm going to go ahead and do the derivative of the first. So the derivative of 2x is going to be 2 times the second plus the first times the derivative of the second. And the derivative of y is y prime, right? Or you can also write dy dx. So I'm going to go ahead and just put y prime. And then finally, for our last bit here, let's see, this is going to actually be a chain rule, right? So I'm going to take the derivative of the outside. So the outside is, hey, stuff's being raised to the 4th power. So I'm going to bring that 4 down, reduce my power by 1, and I leave that inside alone, right? So there's something being raised to that 4th power, and that is y. Then I need to multiply by the derivative of the inside, and so the derivative of y, again, is y prime. And there's, these are very technical things, right? Because we're taking the derivative with respect to x. And so this is why it's dy dx, or we call it y prime for the derivative. But this is why you need to include that chain rule for these, but not for the x's, right? So notice for this first bit up here, I never included the chain rule. In fact, you kind of can, right? So you could kind of say, I'm going to bring down that 2, reduce my power by 1, so it's going to be 2x to the 1st power, and then take the derivative of x, and the derivative of x is just 1. And so you can, in fact, do this, even doing the chain rule with the x's. It's just, I guess we've gotten in the habit of going so quickly by these ones because the derivative of x is just 1. All right, now let's go ahead and we need to solve for y prime, right? We need to figure out, we're looking for the equation of the tangent line. And I guess before I even get into, all this derivative stuff, I could go ahead and write down and get a bit of partial credit here, right? We know we want the equation of the tangent line at the point 1, 1. So I know that my equation of a line has to look like y minus the y value of the point is equal to m times x minus the x value of the point. So in this case, the x value of our point is 1, and the y value of our point is also 1. So we know it looks something like this, and the only question that's left is really, what is this slope? Well, we need the slope of the tangent line, aka the derivative. So that's why taking the derivative is useful, right? The slope of the tangent line is in fact the derivative. So I need the derivative. I need y prime, and again, at this point when x is equal to 1 and when y is equal to 1. And so again, the claim is that you can either solve for y prime, here's a couple of them here, right now, and then plug in 1 for x and 1 for y, or you can plug in 1 for x and 1 for y first. And I find that this is usually a lot easier. It makes the equation a lot cleaner. So that's what I'm going to do. I'm going to plug in 1 everywhere I see an x and 1 everywhere I see a y. So this is going to be 2 times 1 times 1 plus 2 times 1 plus 2 times 1 times y prime plus 12 times 1 cubed times y prime. And so now I can combine my like terms here. Still equal to 0. I can subtract the 4. And I can divide by 14. And so my final answer is negative 4/14. That is my derivative. That is my slope of the tangent line. So I can go ahead and I can plug that into my tangent line equation here. And so I'm going to get y minus 1 is equal to negative 4/14 times x minus 1. And this right here would be my final answer. You don't have to simplify beyond this. And in fact, from me grading this, this viewpoint, it's actually a lot nicer to see it in this form, just because I can really see what is the slope and kind of what is the point that this line's hitting. If you start to simplify and you get it in the mx plus b form, you don't get as much information, if it actually hits this point 1, 1. And so this is the kind of the nicer form, at least for grading it. So this is where I'd prefer you to stop. All right, there is example 1. That's all about our implicit differentiation stuff. Let's move on to example number 2. This is going to be about these rates of change. And I have one of these, a particle moving along with this law of motion. T is measured in seconds, S is in feet, and I have plenty of subparts right here, A through E. All right, so let's go ahead and start with A then. Find the average velocity over the interval from 5 to 8. The average velocity on the interval from 5 to 8. And so average velocity, even though this is coming up and we have these rates of change questions, right? The average velocity was something that we actually first brought up in 1.4. 1.4, we talked about average rate of change and average velocity. So if this right here is given our position, then the average velocity is given by this whole f of b minus f of a divided by b minus a. So this is going to be the equation that I need to use to figure out the average velocity. So let's go ahead. It looks like I have on the interval from 5 to 8. So this is my a and this is my b. And so, okay, f of b. So I need to plug in 8 everywhere I see a t. So, all right, this is going to be a rather large fraction here. So if I plug in 8, I get 1 over 8 squared. That's going to be 64. Minus 1 over 8. So that's my f of b. Now let's subtract away f of a. So if I plug in 5, 1 over 5 squared, that's going to be 25 minus 1/5. That's my 1 over t, my 1 over 5. And then divided by 8 minus 5. And so, okay, let's go ahead and simplify this down a little bit, and I'll show you kind of where I would stop personally, on the exam or on a quiz, and, just start entering it into WebWork. So, first of all, 8 minus 5, that's not so bad. I'm going to go ahead and write this as 3. And then some of these common denominators, some of these fractions, we can get common denominators fairly easy. I'm going to go ahead and multiply this one by 8 on top and bottom, and this one by 5 on top and bottom. So, okay. That way we get to our 25s and 64s. So in this case we're going to have 1 minus 8, so that's going to be negative 7 64ths. And then we have subtracting away, and we have again 1 minus 5, so that's going to be negative 4 25ths. So I'm going to go ahead and make that minus a negative will be positive there. And so now let's see, instead of dividing by 3, I'm allowed to multiply by the reciprocal. So I'm going to multiply by its reciprocal 1/3. And I'm going to write this as just 4/25. I like the positive to be first, minus 7/64. Personally, this is where I would stop, on a quiz or an exam, and I would start typing it into WebWork and whatnot. Let me also say, right, with these ones where you actually have units, it's good to include the units. Every once in a while you can get, half a point or point marked off if you don't include your units. So velocity, and we have feet and seconds. So this is going to be feet per second. So that right there would be my average velocity in feet per second. So yeah, I wouldn't spend too much time, getting all these common denominators between the 25 and the 64 and whatnot. This is how I would leave my final answer. All right, that's part A. Part B, find the velocity at time t. So okay, this is important because, right, we have average velocity versus velocity. Right? And this is velocity at a particular instant of time, right? It's at time t. It's not over an interval. There's no span of time here. It's velocity at an instant of time. So another way to say that is it's instantaneous velocity, and that's exactly what the derivative was for. So I need to take the derivative of this. The derivative of position is going to give me velocity. So okay, let me go ahead and I'm going to rewrite my function down here. And I'm going to do it in a way that, kind of sets me up to take the derivative. So for instance, when I have 1 divided by t squared, that's the same thing as t to the negative second power. So right, you can bring that t squared into the numerator, but it costs you something, right? And the cost is that you have to make your exponent a negative. Likewise, this is really 1 over t to the first power. So again, if I want to bring that into the numerator, that's fine, but it costs me something. Instead of 1 here, I have to write -1. So that right there is going to be my position. So I'm going to go ahead and calculate out the derivative to get velocity. So the velocity is going to be, and now I'm using the power rule, the -2 comes down, and then I reduce my power by 1. Likewise here, the -1 comes down, and then I reduce my power by 1. So minus a negative, I guess I could write plus there. Now, if you'd like to, right, you can go ahead and rewrite this and put it back in fraction form. You can also just leave it as it is right here. But just let's get a little bit of practice here, and I'm going to go ahead and put it back in the fraction form. So we have -2. That doesn't have any exponent here. It's really raised to the first power. And then t to the -3. So I'm going to go ahead and take this, and I'm going to push it back into the denominator using up that negative exponent. So again, it's just kind of the same idea, but in reverse now. Likewise, here we have +1, and I'm going to use up that negative in the -2 and make it +2 by pushing this back into the denominator. So that right there is my velocity at time t. Now it can go on to ask specific times, right, that it would like velocity. So for part C, what is the velocity after 1 second? So I'm going to go ahead and plug in 1 everywhere I see a t. And this is actually nicer maybe with this fraction form over here. So everywhere I see a t, I'm going to go ahead and plug in a 1. And so let's see, I get -2 plus 1, so that's going to be -1. And again, we have units of feet per second. So my final answer here would be -1 feet per second. And I guess I'll highlight this one. This is my other final answer up here. All right. Next up, acceleration after 6 seconds. So, okay, if we want acceleration, that's the derivative of velocity. So I need to go ahead and take the derivative of velocity, and I'm going to look back at this one right here, right, where it already has the negative exponents and it's set up well for the power rule. So let me go ahead and I'm going to use the power rule one more time and take the derivative in order to get acceleration. So the first bit is the -3 would come down combined with the -2. So -2 times -3 is 6. And then I reduce my power by 1. So it goes from -3 to -4. Here, let's see, the -2 comes down, and I reduce my power by 1, and so we get -3. So that is my acceleration at time t. If I want my acceleration at time 6, then I need to plug in 6 everywhere I see a t. So I have 6 times 6 to the -4th minus 2 times 6 to the -3rd. I'm going to include my units of feet per second, or you can say feet per second squared there. And I wouldn't spend too much time trying to simplify this. It can be simplified, and if you want to put it into the fraction form instead of the negative exponent form, you can certainly do that. But WebWork will accept this answer, and I'm happy, if this showed up as a standard response question, you can leave your answer like this. All right, our final bit is E. For time greater than 0, when is the particle moving in the negative direction? So the first bit here is that there's a bit of interpretation, right? We have to convert these words to math. And so this negative direction, right, this has a concrete meaning when it comes to math. And negative direction, right, would mean that your velocity is negative. So if you look at your velocity here, this would be negative. That's what it means to be moving in the negative direction. So if I say I'm, going 5 miles an hour, that would be 5 miles an hour in the positive direction. If I say I'm going negative 5 miles per hour, that means I'm going, 5 miles per hour still, but it's in the negative direction. I'm going kind of backwards from maybe where I'm facing. So, okay, that means that our velocity is going to be less than 0. So that means kind of when I'm going to do this, right, maybe I go ahead and I look at my velocity equation. So, okay, here's E. And I'm going to rewrite my velocity equation, negative 2 over t cubed plus 1 over t squared. And I need to know, when is that less than 0? So when is this less than 0? So now we are back into our algebra days, right? How do we solve inequalities? And so there's a variety of ways of solving inequalities, but the one that I think is really useful for this class, and actually we'll expand upon it quite a bit in chapter 3, is going to be the point testing method. So we're going to go ahead and look at our number line and split this up into pieces, and then we're going to choose test points. And we're going to use those test points in order to see, is it positive there, is it negative there, what's going on. So I'm going to pull this off to the side for the second, and I'm going to go ahead and solve an alternate equation, right? When does this equal 0? So when does this equal 0? So let's see here. I'm going to go ahead and take my velocity and set it equal to 0. So, all right, now I just have an equation to solve, which is a little bit nicer, but still there's fractions and all that sort of stuff, so it's not, great by any means. But for this one right here, probably my first step would be like, that I don't really like fractions so much, right? So I'd like to get rid of all of my fractions, and the way that you can get rid of all of your fractions is by multiplying through by this lowest common denominator on both sides of the equation. So the lowest common denominator is going to be t cubed in this case. So if I multiply by t cubed, and again, so long as I do it on both sides of the equation, right, fundamentally I really haven't changed much. But this actually becomes quite useful, right, because when I distribute that, the t cubed on top and the t cubed on bottom perfectly cancel out. And when I distribute it to this piece, right, well, 2 of the t cubed, right, 2 of them cancel out, 2 of the t's cancel out, so I'm left with 1 t on top. So this is going to be 1 times t, or just t. Now, of course, when you take 0 and you multiply it by anything, you get 0. So this tells me when time is equal to 2, after 2 seconds, the velocity is 0. And 0 is very important, right, because it's kind of the gatekeeper between the positives and the negatives, right? You can't, the only way to kind of jump from the positives to the negatives is to go through 0. And so we found, okay, at time 2, maybe it makes a switch. Maybe it goes from positive to negative or negative to positive, but it definitely goes through 0. And so something could change then. So now this is where we actually need to write down our number line. And again, we're starting off at only time greater than 0. Otherwise, you'd have to be a little bit worried about dividing by 0 here, so that's good. So again, the question specifies for t greater than 0, so you don't have to worry about that bit. And we know that something's happening at 2, so I'm going to go ahead and plop down 2 there and say, okay, I want to see kind of what's happening between 0 and 2 and what's happening after 2, right? And so in order to do that, that's where I say we're going to use these test points. So I'm going to go ahead and choose the test point of 1 and the test point of 3. Now, you could choose different test points. If you really like the value of 1/2, right, you could use that as your test point over here. It's just got to be between 0 and 2. And likewise over here, in fact, I'll change my mind. Instead of 3, I'm going to use 4. So again, anything bigger than 2 in this case. It's just got to be in that piece of our interval. So now I'm going to go ahead and plug these things in, and I'm going to test them, right, with our velocity. So I'm going to go ahead and plug in 1 into velocity. In fact, I already did that, right? That was part C. So part C, I already did this one, and we got -1 feet per second. So this is -1. The big thing here is that it's negative, right? So this is saying that on this piece of our interval, right, this is velocity negative. So our velocity is going to be negative all along here. All right, so that's our first piece. On our second piece, so things that are bigger than 2, right, we've chosen the test point of 4, so I'm going to go ahead and plug that into my velocity equation. So we have -2 divided by 4 cubed, 4 times 4 times 4, that's going to be 64, plus 1 divided by 4 squared, so that's going to be 16. And so again, the big thing here is really, is it positive or negative? I don't care so much about the value here, but is it positive or is it negative, right? Because again, we're trying to figure out when is the velocity negative. So I'm just really looking at the sign of our velocity here. So, okay, we can go ahead and maybe get a common denominator if we wanted to really examine this. So, okay, we have 4 times 16, that's going to be our 64. And so I'm going to get -2 64ths plus 4 64ths. So that's going to be 2 64ths. So that is positive. So that means everywhere bigger than 2, so for instance at 4 we just saw, the velocity is going to be positive. Now notice I'm always plugging these back into the velocity equation because it's velocity that I want to know, is it positive or negative. We want to know when is the velocity negative because, right, that's when the particle would be moving in the negative direction. So according to my results here, we see that between 0 and 2, we have it's negative, the velocity is negative, so that I like, and then after 2 it becomes positive. So that's not going to be in our answer. So in this case, the velocity is negative. Our answer here is going to be on the interval from 0 to 2. And remember, at 0 we're not including because you'd be dividing by 0, and so the problem even specifies, you know, t should be greater than 0. So that's why we don't use a bracket for that one. We don't use a bracket for the value 2 because at 2 it's actually equal to 0, right? We actually solved this back here. When time is 2, the velocity is equal to 0, and remember we want it to be strictly smaller than 0. We want it to be a negative number, and so that's why we don't include that one either. So you're going to use parentheses for both of these. So on the interval from 0 to 2, that's when our velocity is negative. That's when our particle is moving in that negative direction. All right, that's the 2.7 question about these different rates of change. Let's go ahead and move on then to example number 3 with our related rates. And in this one, I chose a particularly difficult one. I wanted to make sure to be on, you know, at least the medium to, you know, hard side of things. This one has shown up on some previous semester's exams, you know, during like the academic year and stuff like this. So just an FYI, it is on the tougher side, but it is exam possible, I guess, right? It could show up. So a filter filled with liquid is in the shape of a vertex down cone with a height of 3 inches, a diameter of 2 inches, and it has an open upper end. The liquid drips out of the bottom of the filter at a constant rate of 5 cubic inches per second. How fast is the level of liquid dropping when the liquid is 2 inches deep? All right, so there's a lot to take in here. The first thing I'm going to do is try to draw a picture. We have a vertex down cone. So I'm going to go ahead and draw a cone with the vertex, the point going down. So we have something like this. It has a height of 3 inches. So, okay, this bit right here should have a height of 3 inches. It has a diameter of 2 inches. So if I go all the way across here, the diameter should be 2 inches. Liquid is dropping out of the bottom of this filter. Okay, so it's kind of like a coffee cup or something like this. Maybe there's some liquid inside here, and the liquid's going to kind of take the shape of this, you know, physical filter here. So, and it's dripping out of the bottom. So there's a little hole here, and it's dripping out. And so this little cone here that's made out of the water is actually losing height. Okay, it says here that, let's see, the liquid drips out of the bottom of the filter at a constant rate of 5 cubic inches per second. All right, so we have to figure out what kind of math thing is this, right? So it's a rate of change. So it talks about a constant rate, how fast the liquid is dripping out. So it's going to be a derivative. These rates of change, the instantaneous rates of change are going to be derivatives. And so, okay, it's derivative of something. We need to figure out what is it the derivative of. Well, it's the amount of liquid that's, leaving the filter. Another hint here is this cubic inches. So this is actually going to be volume, the derivative of volume, right? Because cubic inches will tell you the volume, maybe of water that's inside of this filter, and the fact that you have 5 cubic inches per second leaving it, right? That's going to tell you how the volume is changing. So what is the derivative of the volume? So I'm going to go ahead and write V prime, the derivative of the volume, is equal to, and I'm going to put -5, right? Just to say that, right, the liquid is actually leaving. You don't have a positive volume change, right? Water is not being added to it, right? But actually water is leaving. So the fact that it's dripping out, that it's leaving this filter, right? I'm going to call this -5. And again, this is cubic inches per second. And then in order to win the game, at the very end here, we get the question, right? So it's asking, how fast is the level of the liquid dropping when the liquid is 2 inches deep? So, okay, as this kind of drips out, you can imagine that the height of the water cone here, right, that this is going to be changing. And it wants to know how fast is the level of this liquid, this height right here, how fast is that changing when the liquid is 2 inches deep? So at a very specific time, the height of the liquid there is going to be 2 inches deep. Now it's not always 2, right? But maybe at one point it will be 2, right? And it wants to know how fast is it changing? What is the rate of change? So in order to answer this question, we need to know what is the derivative of this h, the height of this liquid here. How is this changing? All right, so we have now our setup. We've converted all of these words into math, and this is sometimes the hardest part, is really to sit down and read and reread several times in order to convert these into equations. Now I need to go ahead and think about, well, how can I relate, right? I know how the volume is changing here, and I want to know how is the height changing. So I need to relate these rates together. AKA, it's a related rates question, right? So this is why this is a 2.8 related rates question. And I have to figure out, okay, I have a cone, I have volume, I have heights. How can I relate these things together? And so let me go ahead and jump back really quick. And we're going to look at our formula sheet. So we'll suppose that we're, on the exam and whatnot, and see what on the formula sheet could be useful. And the claim is there's a whole section about geometry equations, so things that could be useful. So here, geometric, we have area of a circle, we have circumference. Okay, those not so much. Let's see, we need stuff with volumes. I don't see volume, I don't see volume. Nope. And then, down here, volume of a sphere. Well, we don't have a sphere, so that's not the one. Let's see, surface area, not so much. Volume of a cylinder / prism. All right, but we have a cone. So volume of a cone. So this very last one here, volume of the cone, 1/3 height times the area of the base. So let's go ahead and write that down. So volume is going to be 1/3 times the height, which I've been using h to denote height here, times the area of the base. Well, the base of the cone here, this is a circle, right? So I'm going to go ahead and use so this is area of a circle. So area of a circle, and if I go back here one more time, I think that one's on there too. Area of a circle, yes, pi r squared. So let's go ahead and use that. So this is going to be pi r squared. So we actually had to combine a few of these formulas together, but it's nice. We see now we have our v and we have our h. But we have this extra thing, this extra r that I don't really like so much, and so I'd like to somehow get rid of that. Get rid of the r's and make it so that we just have h's. Because again, right, the way that we answer this is all with this, okay, how is the height changing, right? What is the derivative of height? So, okay, the r's aren't really so important. I don't have any information with r's here, and so that's why maybe I want to get rid of this one. Okay, so, well, the last thing that I haven't really used that maybe I can get rid of this r, right, is there was this whole business I see over here. There's a 3, there's a 2, and there's this h, and I haven't really used these in any kind of meaningful way yet. So let's go ahead and try to use those to get rid of these r's. So, okay, The big thing here is that actually there are some embedded triangles going on. So I went ahead and I did them with just dashed lines, but if you put it right on here, so this is again length 2, and this triangle right here, this height would be 3. And then if we look at the water triangle here, so okay, this is some diameter all the way across. I'm going to call this D. I don't know exactly what it is. And you have to be careful, right, because this is actually changing. Water is dripping out of this, so you're going to be losing water. And so actually this is, as it goes down, right, the diameter is going to be changing. It's going to get smaller and smaller. And likewise, the height will be changing. So I'm just going to go ahead and I'll draw this in, but I'm just going to call it H because, again, we want to know how fast is this changing. So this picture is getting kind of messy. I like to sometimes pull it off to the side here and just kind of recreate the same picture, but with a little less mess. And you can see what we have here is actually some similar triangles. So similar triangles, this is where, again, we have some formula back here. So if triangle ABC is similar to triangle DEF, then the ratios of their side lengths are equal. So that's the big thing that we need to use with our similar triangles. So I'm going to go ahead and say the diameter of the large triangle here, so 2 is to its height 3, is the same as our water triangle. So its diameter is D, it's changing, and its height is H, again, it's changing. So this ratio of side lengths must be equal. So 2 is to 3 as D is to H. So again, kind of the fact that this filter and the water, these cones kind of together, right, form these similar triangles. This is what gives us this equation. So let me go ahead and rearrange this a little bit. And I'm going to write 2/3 H is equal to D. So, but remember, I have R, I have radius, and I've been working with diameter, right? So this is where I need to kind of use that the diameter is just twice the radius. So I'm going to go ahead and substitute that in. So I'm going to write 2/3 H is equal to twice the radius. Now these 2's can kind of cancel out nicely, and you have R is equal to 1/3 H. And so now, right, I've done all this work in order to try to get rid of this R right here. So now I can get rid of this R because, again, right, all of my information that I want is about H's. Really, I don't have anything useful for R's. So I'm going to get rid of it. And the way that I do this, right, I did all this work to find my exchange rate. A radius is worth 1/3 of the height. So that's kind of the way that I'm going to trade this in. So, okay, volume is going to be 1/3 height times pi times 1/3 height, and the radius has to be squared. So again, the radius is 1/3 the height, and I need to square that because it's R squared. So now let's go ahead. You have to be a bit careful here when we're simplifying this down. So 1/3 is also inside of the squaring, right? Because it's the radius squared, so it's the entire radius, and 1/3 is included in that. So when I square 1/3, I get 1/9, and when I square H, I get H squared. One more line, then I promised we're going to do some derivatives. 1/3 times 1/9 is going to be 1/27. This pi is also constant. It's along for the ride. And then our variable here is this H, and it looks like we have 3 of them. 1, 2, 3. So, okay, now we have our volume equation set up. It has just H's. We're ready to take the derivative and hopefully start using some of this other information that we have. So let's go ahead and take the derivative across the board here. V prime is equal to 1/27 pi. These are all constants. And when I take the derivative of H, I get 3H squared. And then we need to multiply by the derivative of the inside because we're taking technically a time derivative right here. So this is going to be dH dt, or that's the same thing as H prime. Which is quite good because we want to solve H prime equals. So if your equation didn't have any H primes in it, that would be rather alarming. All right, we have our our volume, and how this is changing is at -5 cubic inches per second. So now I'm plugging in this. I also know that H is going to be equal to 2 at my time that I'm interested in. So let's see, 1/27 times pi times 3, and everywhere I see an H I can put a 2, so 2 squared will be 4 times H prime. And now I can solve for h prime. In fact, there's a little bit of cancellation that I can do here. 3 and 27 will cancel a bit and give us 9 in the denominator there. And so let's see, I'm going to go ahead and multiply through by 9 on both sides. So that's going to give me negative 45 on my left-hand side. I'm going to divide by pi, and I'm going to divide by 4. Actually, let me do that in the other order. I'm going to divide by 4 and divide by pi there. So now notice I've moved over this 9 to the other side, I've moved over the pi to the other side, I've moved this 4 over to the other side, and so all that's left on the other side is h prime. So in this case, right, this is telling me again, how is the height of this cone changing? And it turns out to be negative 45 over 4 pi. And again, whenever you have units, you should include units, otherwise you can get, a point or so marked off. And so let me go ahead and include units here. And let's see, I think it was inches. We had a lot of things with inches. Yeah, 2 inches deep, 3 inches. And since it's a derivative, how it's changing, right, we need inches per. And it looks like our time units were seconds, right? So inches per second. So this height is going down this amount of inches per second. So that right there would be my final answer. Again, this is certainly on the more complicated side of things. It's an upper level related rates questions, but I have seen this before on exams. And so I wanted to make sure to kind of give you one that was, a bit on the harder side. All right, 3 questions down, 1 to go. As I promised, this is a long video. But again, with the exam coming up, I think it's worth it. So let's use linearization to approximate the square root of 24. Now this one's not going to be nearly as bad as our last one was, but again, it is kind of on this harder side of linearization questions. One thing that you will have noticed, right, is that the linearization equation that we got in the notes is not on the formula sheets. So you do need to have this memorized. Oops. And it goes, the linearization is equal to, and we can do f of a plus f prime of a times x minus a. So it's very similar to our equation of a line. In fact, the linearization, it is an equation of a line. But notice we need to find some specific things, right? We need to know what is a. Then we can plug it into our function. And then we also need to know what is the derivative of the function at a. The problem here is that, right, this is what I have, the square root of 24. It didn't mention what is our function, right? So the question is, well, what is this function that I need to take the derivative of? And also I need to know what is a. Is 24 a, or is it something else? And so these are the big things that I need to figure out first before I start my work on this question here. All right, so the answers to these, and again, I definitely recommend that you pause the video and guess on your own. But the answers are, the function here should be the square root function. So again, because we have the square root of 24, kind of the most interesting function that's acting on our numbers is the square root function. And so this is the thing that we're going to want to find the linearization of. And a is not 24 actually. It turns out to be 25. So why you choose 25 is that it should be close to the value that you're trying to approximate, but it should be easily plugged in to our function. So the square root of 24, I don't know exactly what that is, but I do know the square root of 25. All right, the square root of 25 is just 5, and so because this can be easily plugged into our function, right, that's why I'm going to choose this to be my a value. And it needs to be close to the number that we actually want to plug in. So I would love to plug in 24 and figure out what this value is, the square root of 24. However, this is a bit difficult, and so I plug in a number that's near this, 25, that I do know the square root of, and then, right, I'm going to use this linearization equation. So that's why you would use 25 and not, let's say, 16, right? Because 16 also has a great square root. It's just 4. But it's not very close to 24, right? 25 is a lot closer to 24 than 16 is. So that's why you're going to be using 25. All right, so let's go ahead and now we can start plugging these things in. So for instance, I can figure out f of a. So f of a, f of 25, that's just going to be the square root of 25, and that's 5. Great. We also need f prime. So I can go ahead and take the derivative. The way that I do that is right by rewriting this. Instead of the square root, I'm going to write it as x raised to the 1/2 power, because this I can use the power rule on, right? So I'm going to go ahead and use that power rule. bring the 1/2 down, reduce my power by 1. We get something like this. In fact, let me go ahead and simplify this and put it into its fraction form. So with that negative exponent now, remember, you can get rid of that negative exponent by pushing it down into the denominator. And x to the 1/2 is the same thing as the square root. So I'm going to go ahead and write it like this, the square root of x. Now, again, we want f prime at our a value. So f prime at our a value is 25. And again, notice that we have another square root here, so it's really easy to plug that in. 25 goes nicely into square roots. And so, okay, the square root of 25 is 5, so 2 times 5 is going to be 10. So I get 1/10. Notice why I put it back into its fraction form here is that it's a lot easier to plug in 25 into this than maybe it is up here, right? 25 raised to the negative 1/2, that's a bit more daunting of how do I simplify this? You know, what is 25 raised to the negative 1/2? But if I have it in its fraction form, it seems to come a bit easier. All right, now I'm going to go ahead and I'm going to find my linearization equation here. So I have L of x. This is equal to f of a, so f of 25, that was my 5, plus f prime of a. So here was my work here, the derivative, and I plugged in my 25, so I have 1/10, times x minus a. And my a value, again, is 25. So that right there is my linearization equation. And we want to use this linearization equation in order to solve what is, or approximately what is the square root of 24. Now I know it should be around 5, right, because the square root of 25 is 5, but it's probably a little bit less, right, because 24 is less than 25. So let's go ahead and plug in. Again, I'm interested in 24. So I'm going to plug in 24 everywhere I see an x, and I get 5 plus 1/10. And then 24 minus 25, so 24 minus 25 is going to be negative 1. So that's going to be 5, and let's see, plus negative 1 over 10. So I'd probably write that as 5 minus 1/10. So again, this is great to check our work. It's a little bit less than 5, right? So it's 5 minus 1/10, right? So this seems reasonable to me. And just an FYI, if you were to put this in decimal form, right, 5 minus 1/10, that's going to be 4.9. That's 1/10 smaller than 5. And if we go ahead and we use a calculator here, and I'm just going to use my browser up here, the square root of 24, we get 4.8989. So actually that's really darn close to 4.9. Right? If you were to just round here, that actually, so this is a good approximation, right? So this is actually doing a good job. We know it's close to 5, but it's actually really, really close to 4.9. All right, well, with that, we're done with the problems for today. Again, make sure that you're putting in a few hours today studying before the exam. It should be tonight, again, 7 to 8:30. I'll go back up here and flash this one more time on the screen, right? B122 Wells Hall. Again, we're starting at 7. I would arrive a bit early just to make sure that you get a good seat and you find it and you get parking and all that sort of stuff. So arrive a little bit early. But yeah, I'll see you guys tonight and good luck.